Hello everyone. This is going to be the second installment of the engine build series that I'm doing. This one we're going to be measuring out the cylinder bores, looking for taper out of roundness and overall wear to see what condition the cylinders are in, whether or not they can just be honed here at home into spec to use standard pistons and rings, or whether it needs to go to the machine shop and have an overbore done. Again, I'm thinking it's probably going to go to the machine shop anyway and have a 30 over done on it, but just for my own education and hopefully to educate any of you that are watching the video on how this process goes, I want to measure it out and see what the tolerances are and what we have to work with the block as it stands now. Now, to measure the cylinder bores, you need some tools, obviously. You will need either calipers. These are digital calipers, or a micrometer that is big enough for at least 4 inches. This one isn't. This is the only mic I have, and it's only good to 3 inches, so I'm not going to be using this. I'm going to be using the calipers. What you're going to be using them for is to set the depth on your dial bore gauge. This is the tool you'll actually be using to measure the deflection of the cylinders. Now, this tool here is not a direct measurement tool. You can't slide this into a bore and have it tell you how big the bore is. This is what you would call a variance gauge or a differences gauge. This has to be calibrated down here to the depth or the width, however you want to look at it, of whatever it is you want to measure. So that you're going to use the micrometers or calipers to set this, and in this case the bore from the factory is supposed to be 4 inches. Specifically it was like 40001, but we're going to set this to 4 inches using the calipers. Then once that's zeroed out to 4 inches, you're going to move the dial, the ring indicator on the dial bore gauge, to wherever the needle is pointing, and it's going to point wherever it lands. You have really no control over it, but you can reference 0 by moving the dial and lining it up with that arrow. That will show you whatever moves now on the needle is going to be the difference between 4 inches and what you actually have. So if I slid this in the bore and it deflected to the left, where the one mark is, the larger one, that is 1/100th of a millimeter. This is a millimeter increment dial bore gauge. I wish I had an inch measurement one, but I don't. So whatever measurements I take with this, I need to convert to inches when I'm done. But wherever it lands, I will show you bigger or smaller than what you set down here. So we're going to take that, get it set, and then we'll go to the block and we can measure out the cylinders. There is one other tool you can use. This is not as accurate, but it can do in a pinch to get you some gross measurements, to give you a ballpark figure. This is a T-handle gauge or a plunger style. And this was an inside diameter measurement tool, and you would simply slide it in the bore, and then these plungers will collapse to the dimension of that bore. Then you lock it down at the handle. Then in the reverse order of what you would do to set the dial bore gauge with calipers or a micrometer, you would use calipers or a micrometer to measure whatever this is, and that would be the diameter of the bore that you measured. This is, it can come in handy, especially if you don't have the probes necessary for a small diameter to get into a space with your dial bore gauge, a smaller journal size. But in reality, if you have a good dial bore gauge and calipers, you won't need this to measure a cylinder. But I wanted to show you that anyway. So I'm going to go ahead and get the tools set up on the bench the way I need to and show you how to set the dial bore gauge. Okay, so I have the bench set up here. Ideally, you would have a bench vise. You could clamp your micrometer or calipers in, but I don't have one right now, so I'm just using this carpenter's clamp I had. But I'm clamped to the table, and what I have done is I have set the calipers to 4 inches exactly. So when I take the dial bore gauge, this end of it, there's a tiny plunger on the back, and then of course you have the probe end. The probe end is static. It's locked down with this jam nut here, but this is what's going to actually do the measuring part here. So what you have to do is get the plunger inside the calipers or the mics. I'm going to stop saying either or. I think you get the gist of it now. And then you're going to roll out. You're just kind of move it back and forth in both axes, up and down, left and right, to make sure it centers the needle at the measurement. And then you're going to come up. Do not take this as being this difficult. It just is with one hand. You're going to come up here and you're going to see where the bore gauge is registered on the needle. So let me get this stabilized. Right now it is pointing roughly at 10, 11. I'm going to put the camera down real quick and I'm going to go ahead and center this and then roll the needle to 0, and I'll show you how that measures up once we're in the calipers. Hold on one second. Okay, so I've got that centered up. I'm going to go ahead and slide it back into the calipers and get this. I just want to show you that it is set to 0. So there you go. I've got them centered and you can see it's kind of walking a little bit, but it is set to 0. So now we can go over here and now you have your cylinders. This is the left bank. So driver's side, the cylinder 1, 3, 5, 7. You start in any order you want. Just make sure you keep track of your measurements with a notebook, or as I've done, I've got a little whiteboard and I've just made circles and numbered them. Now, you saw there's other numbers there. I've already measured all these out and done the conversion, so I didn't have to stress on that while I was doing all this. But what you will do, starting at either 12 o'clock or 12:06 or 3:09, you need to take 3 different measurements in 2 different axes. So I usually start at 12. Or I've been starting at 12. I can't say usually because I haven't done this a lot. But once you get it in towards the top, you're going to rock it back and forth until you see the maximum deflection on the needle. And that's going to be your depth. This is just under 6. So I would call that like 0.065 millimeters. Then you'll move down halfway through the cylinder, do the same thing. This is coming in right at 2-ish. So 0.02 of a millimeter. Do the same thing at the bottom, not the very bottom, but about a third way down. That's coming in at about 1/1000. So those are your measurements going this direction. Then you're going to come around 90 degrees to that. Do the same thing at the top. Get it going here. I think I may have lost my calibration. Let me get this right here. Nope, I was just hung up on the ring ridge. That's why it was reading so off. You want to, if there's a ring ridge in your cylinder, you want to make sure you get below that, because that's really not the measurement you want, because that's going to have to come out no matter what you do. So this one's walking back and forth right to 5. So that'd be 0.005. Move halfway down. Rock it back and forth a little bit. This one's coming to about 1/1000 in the middle. Go down to about 2/3. And look at that. Landing right on 0. So there's like no wear this direction in the cylinder at the bottom third. So, and that happens, you know, some of these surfaces just don't get worn on because there's no thrust going on them, or the piston, or I have the dial bore gauge set right now is actually below where the piston ever traveled. We'll move up a little bit and it's just like half. So that'd be 0.005, 0.0005. So that's actually an accurate measurement. There's just simply no wear in that position of the cylinder. I'll go ahead and measure cylinder number 5 here. Rock it going up towards the top, but making sure I'm not on the ring ridge. It's walking out to about, we'll call it 5. So 0.005, move halfway down. It's actually a little under 1/1000 there. Move down a little more. Call that, it's looking like a little over 1/1000. So there's a little bit of, well, they're all uneven. All wear is uneven between cylinders and even inside cylinders. This one's actually got a little bit of an hourglass shape to it. It's wide at the top, gets narrow in the middle, and then widens out a little bit at the bottom. I guess that can happen. I could think of reasons why, but I'll offer up my opinion on it, I guess, and that is that the middle of the piston isn't really under stress like the bottom and the top when the crank is being pushed on by either the combustion stroke or when it's coming up on the compression and exhaust strokes. It's possible that the bottom and top wear more unevenly than the middle. All right, so we're in cylinder number 3 now, right at 5 thousandths. That's the lateral dimension, the parallel to the engine block front to back. So go down halfway here. It's coming out a little over 4. When you see something like this, and I ran into this is why I wanted to do a bunch of practice with this gauge before I got on the video. It's possible you've lost the calibration on your dial bore gauge. So what you got to do is you just got to come back to your calipers or your mic and recalibrate it, which I'll do here in just a second. You want to make sure the lock ring for your probe is tight. That's usually what happens, is that lock ring will come loose and your probe will walk out because it's just threaded in, just like a screw coming undone or a bolt. So yeah, I've lost about 1/1000th of my calibration here just from using it so much. Set it back to 0. Okay, we come back over here. I think we're on cylinder 3 middle. Yeah, okay, so instead of going over 4 now, you can tell it's right where it should be. It's giving me a good reading. About 15 thousandths. Go down to the bottom. Let's see what we get here. You want to try to square it in the bore as much as you can. And I don't think I'm really square there. There we go. We're going to call that 25 thousandths. And we can go to 90 degrees towards the top of the cylinders, the way they orient. So at the top of this one, we've got about 25 thousandths, 25 hundredths of wear. Go down to the middle, it's about 2 hundredths. And then go down to the bottom, call that, just because you don't want to write 0, 0, 0, we'll call that 1/2 thousandth. All right, in cylinder 1, walk over here. Move this in. It's coming out to about 4 hundredths. Remember, these are in millimeters. The inch measurement's going to be much smaller. That is about 3 hundredths. And then at the bottom, again, probably like 28 hundredths, but it's 3. We'll call it 3. You can extrapolate based upon the needle position between halves, quarters, if you want to get really specific with it. This isn't digital, so you do have to put some interpretation into where the needle lands. All right, going the other direction, we've got about 55 hundredths there. Midway through, we got about 1 hundredth. And then at the bottom, we've got about, it's hard to do the bottom because it's harder to judge whether you're square in the bore. I'm going to call that 25 hundredths there. So that is what we have for wear across all these cylinders. So that would give you your taper. Excuse me, I'm going to set this on the tripod again here and sit down. Now those numbers are just numbers unless you know what they represent, and through this process I've been learning what they mean. What they're going to show you is the amount of taper and run out or ovalness of the cylinder. Taper would be best described as a cup, a tumbler that's narrower at the bottom and wider at the top. Your cylinder takes that shape over time. Because of the way the thrust surfaces on the piston, the thrusting on the piston from the combustion cycle exerts the force into the side of the piston wall unevenly. And that's because, well, there's 2 reasons. One is your combustion event doesn't exactly happen at top dead center. It happens before top dead center. That's why you advance timing. The reason advanced timing makes more power is because you can get a more complete fuel burn because the spark event happens sooner and the flame propagation is able to reach its maximum power, its maximum fuel burn, aka pressure, on the cylinder, on the piston, at top dead center. So you want the maximum force pushing down on the cylinder while it's vertical. If that event happens earlier or later, the crank is going to be tilted in its rotation one way or the other. When that event happens, therefore, the pressure on the piston will follow the inside of that angle at which the pressure event, the combustion event occurs. So you can imagine a piston wall here. The piston, because it's on a wrist pin, may start vertical. It's always going to be vertical on the cylinder wall, but it is on a lever, which is your rod, connected to the crank at an angle. So the crank's going to be coming down like this or up like this, depending upon which cycle it's on. The pressure from that event in the cylinder, whether it's the exhaust or the more likely to cause stress, the combustion cycle, is going to exert force on the piston a little bit unevenly, leading you to wear in the cylinder walls. There's also just the general wear of the piston rings over time. It's just eating away a little bit of the cylinder wall over time. This motor here is a 73 block, and I have no idea how many miles on it, and I am very thrilled that the pistons are cylinders are in as good a shape as they are. This block here, I'll show you the measurements that I got when I translated them all into inches, indicate to me that with getting a ring ridge remover, which you can rent or buy, just to get that little top part where the wear never happened because it was literally nothing touching the cylinder wall, that's about in the first quarter to 3/8 of the top of the cylinder here. Nothing ever wore on it because no metal was ever in contact with it. The piston ring stopped. It's kind of piston top, piston ring. There's a gap there. The ring's the thing that is making contact with the cylinder wall. It never wore that area. Well, that leaves a ridge. And if you're trying to get your pistons out through the top, which is the proper way to do it, when you're disassembling a motor, you may not be able to push that piston out because the rings are going to hit that ridge and it'll just stop it. So there's a tool for that. It's called a ring ridge remover. You put it in there and you just move it around with a wrench, and there's a cutting blade, and it just eats away that ridge, makes the cylinder wall square again. So I could get one of those and use it on this motor, and then use a stone hone or a ball hone or both, and try to get the taper out and also get the ovalness out of it, and use standard rings and pistons. And this block with the soap and water bath and some scrub brushes and everything else would be ready to go with maybe not even going to the machine shop. So that's what the backyard rebuild is. That's what your ring rebuild is. You pull the pistons out, put new rings in it, maybe give it a quick hone with the stones and everything, and throw it back together with new bearings. I'm not going to do that with this one. This one's going to get a proper rebuild 30 over. So here's where the numbers looked on here. Let's just take his cylinder 1 because 1 is 1. At the top I had 18 thousandths of an inch of wear on the, this would be the parallel side to the engine block going this way, and 23 thousandths of an inch of wear on this side. Your wear should always be greater perpendicular to the block because that's the way the crank is moving. The crank doesn't throw the piston this way, it's pulling it down this direction like this, if you can get the gist of that with my hand signals. But anyway, so this has taper. You see it went from 23 thousandths at the top to 15 thousandths in the middle, and then 15 thousandths at the bottom, so that taper is minimal. It went from 18 thousandths at the top to, call it, goodness gracious, I don't think that measurement's right. I think that's supposed to have one more zero in it. No, that's right. Call it 1,000th. And then a little over 1,000th at the bottom. So that has a little bit of hourglassing in it. But man, when you're using the style bore gauge, it's the variance in the way you're reading the gauge could easily be the difference of these numbers right here. So that cylinder is actually in really good shape. Cylinder number, I'm trying to remember when I measured this. I think cylinder number 7 was my worst one. Just looking at these numbers here. So I had like 3 thousandths of an inch of wear at the top on one surface and the other, and then still had 2 to 1/1800ths in the middle and 15/1600ths at the bottom. That cylinder is worn more than any other one of them for some reason. Now, my understanding again is that, just going by the internet, what I've read, what I've watched, you can get away with about 0.5 thousandths of wear. So that'd be 0.005, and still use standard rings. If it's over that, you'd want to really, really hone on it till you got closer to 1/1000ths, because they make a ring, like a thousandths over ring kit that will seal up a cylinder up to 1/1000th of an inch, and you don't have to take it in for honing. If it was everything the recommendations I've had from all these people who are experts that I've watched and talked to and read, 1/1000 is all you want to use. If you're over 1/1000ths, get it bored. I'm not, but I'm well under. The most I have is 3/1000ths, so I could do the hone and rings and get away with it. Still, as I mentioned, I'm not going to do that. I'm going to go ahead and have the 30 over done on it. So that brings us to what the next event in the series will be, which will be getting this to the machine shop. I got a quote from one machine shop here locally for just align honing, boring, cleaning, the basics, freeze plugs, cam bearings installed, is about $600. Seemed a little high for that level of work. I asked about some other services they do, like doing or could do clearancing for a stroker and putting in splayed mains, because I only have 2-bolt mains. I could get splayed caps drilled in, but they said they don't do that. So I'm going to find another couple of machine shops to talk to and see who has the best deal and who can do the most detailed work, like doing that clearancing or installing splayed mains if I decide to go that direction. But I'm going to close this video out now. I hope you learned something. Please comment, like, and subscribe if you have any questions about how I went about this. I will mention that everything I've learned is through reading and watching the internet and self-education. Never had specific teaching by anybody on doing this. I do believe my practices are right, and I'm confident with the measurements that I took and the way I'm operating the equipment, so I'm going to go with those numbers. But if you have questions, put them down in the comments. I'll try to answer them. And I want to thank specifically a couple videos or people that you could watch that explain this in better detail, and the video may show a little more detail on setting up your gauge. And there's a channel called Pete's Garage. Very good. That guy's amazing. My Vintage Iron is another guy who does engine build videos, and Eric the Car Guy did a good series on engine building, and Nick's Garage, which is a weekly series. He posts videos on Monday. He's an old Mopar master, but you learn a lot from any engine building by watching him and listening to what he has to say. Those are the main videos I watch, and then I just read other articles and threads to get the rest of the information. So I'll close out. Please like and subscribe. I will talk to you and hope next time, and hopefully I'll have a bright, shiny block fresh from the machine shop.